I'll talk today about the kinetic theory of gases. My name is Rodrigo Albuquerque. In outline, I will show the motivation to study kinetic theory of gases, the methodology. I will show basic assumptions to be able to calculate the pressure, and finally, I will show a relation between temperature and kinetic energy. I'll show an exercise, and then I will review the main concepts and show the references. In the last class, we have seen the equation for the ideal gas, which shown here. We have the pressure multiplied by the volume equals to the number of particles N and the Boltzmann constant K multiplied by the temperature T. But how can we relate macroscopic and microscopic properties of gases? The macroscopic are pressure, volume, and temperature, and the microscopic are given by positions, for instance, of the individual molecules and or velocities of individual molecules. This is an important issue since it allows us to predict, for instance, the temperature by knowing the velocities of the molecules inside the gas. Let's first simplify the system. So we have a gas in a balloon. Let's represent the system as a cubic box of dimension L, shown here. And we have some basic assumptions to do. Molecules do not interact with each other, just like in the ideal gas case, except during collisions. So the molecules can collide with each other, and they can collide with the walls of this box. Collisions are elastic, which means the linear momentum is conserved. In this case, we see a molecule is going to collide with this wall, and before collision it has velocity Vx, just x component is shown here. After collision, the velocity is minus Vx, so the energy is conserved. And just the velocity changes the direction. And the molecules have random velocities, as you can see here. The properties are isotropic, which means the properties do not depend on the direction being analyzed. So the properties in the x direction, y direction, and z direction are the same. These molecules can move in a straight line until the next collision. Now, let's see how to calculate the pressure using the assumptions shown previously. First, to simplify the system, let's consider just one single molecule inside this box. And let's consider just the x component of the velocity. Let's try to calculate the pressure on this specific wall on the left side. Pressure may be given by force divided by area, where the area is straightforward to calculate, is L squared. The force can be given by the Newton's second law, which is shown here, and this Newton's second law can be modified, can be put in this form, where we have here the variation of momentum. Momentum is mass times velocity, divided by the variation of time. In this case, we can write force is equal to the variation of momentum, which is mass times velocity, divided by time. And since the mass is constant, it goes outside this delta. So we have here mass of the molecule multiplied by the variation of velocity, just x component is shown. That's why we have the x component of the force here, divided by the time. Before collision, the velocity of this molecule shown here in this cartoon is minus Vx. So when it goes to the left, the velocity is minus Vx. When it goes to the right, is Vx. So before collision, the molecule has a velocity minus Vx. After collision, it has Vx, which means the delta, the variation in Vx, in velocity, was the final velocity Vx minus the initial velocity, which is minus Vx, which means delta Vx is 2Vx. We can now substitute Vx, this delta Vx, in the equation 1 here to get equation 2. Now let's think about the time interval between two collisions. Just remember that the collisions are responsible for the pressure on this wall. So when the molecule first collides against this wall, it would bounce to go to the other side and will collide with this right-hand side wall. It would collide and would go again to the left. So the molecule would walk L and then L again until it reaches again this wall. So the distance traveled by this molecule is 2L. And if we use the very simple relation between velocity and distance traveled, which means velocity equals to distance divided by time, we can calculate the time, which is distance divided by velocity. In this case, equation 3, we can now take the delta t and substitute into equation 2 to get equation 4, which shows how the x component of the force is given as a function of the x component of the velocity. Now we have just used one single molecule inside this box and just the x component of the velocity. Let's expand this concept to consider many molecules. Let's consider n molecules inside this box. All of them have the same mass, and let's still keep just the x component of the velocity, Vx. In this case, we have many particles, and each particle has its own component of the Vx. Vx1, Vx2, and Vxn, for instance. In this case, equation 4 would be rewritten to take into account the components of the velocities of all particles, of all molecules here. So Vx1, Vx2, Vx3, and so on until Vxn. We have here n molecules. This is a summation of the velocities, of the square velocities of all particles, which is represented here. The summation is run over n particles. Now we can divide equation 5 by the number of molecules inside the box, which is n. So we divide the left side and the right side by n, and we get this expression here. And then we can realize that the summation over n velocities divided by n is just an average of the square velocity. And so I'm representing the average using this bracket notation. So this represents the average square velocity, which means I can simplify this equation in this form in order to get equation 6, which shows how the x component of the force depends on the average square velocity of all particles, of all molecules. Now let's recall that properties are isotropic as one of the basic assumptions I did in the beginning of this lecture, which means the average velocity in the x direction is the same as in the y direction, is the same as in the z direction. There's no reason why the molecules would be, the average velocity of all molecules would be higher in the x direction than in the y direction. All of them are equal. And if we would like to calculate the total velocity, we have to sum up all components. We have to sum up Vx plus Vy plus Vz. When you do this, we can see that the total velocity is just the sum of Vx, Vy, and Vz, which means one single component is just the total velocity divided by 3. This is straightforward to show. And then we can substitute Vx in this expression, equation 6, by this expression here. So now we don't have x component of the force, but we have the total force, and related to the average velocity of all particles, of all molecules. So finally, pressure is equal to force over area. Area is here, and the force which I have just calculated in the previous expression. If we divide force by the area, we get this expression here, where we should recognize that L to the power of 3 is just the volume of the box. So we have here the volume. And now we can put 3V to the left side of this equation. We get then 3PV equals to this quantity. This is equation 8. Now we can take equation 8 and divide it by 2. We have this expression here. And once more, we have to recognize that the mass multiplied by the square velocity divided by 2 is just the kinetic energy. In this case, we are taking the average of the velocity, of the square velocity, and that means we don't have a kinetic energy, but we have the average kinetic energy, which we are representing using this bracket notation. And finally, if we isolate PV in one side, we have PV equals to this quantity. If we recall from the last class that the ideal gas is given by this expression, this equation of the ideal gas, we see that PV equals PV. So the right side of both equations are also equal. And by equating NKT NKBT to the right side of this equation, we get the final expression, which is most expression of the lecture of today, which shows how the average kinetic energy is related to the temperature. So this is the expression we wanted to find, which shows how a very important macroscopic property like the temperature can be given as a function of the microscopic property, the average kinetic energy, which is given by this expression, which can be written as a function of velocities. Now we can make an exercise. Let's calculate the increase in the average velocity of argon when it's heat up from 300 to 400 Kelvin. Adopt ideal gas behavior. This we can discuss this exercise in the next lesson. Let's revise the main concepts. First, we have seen that gases have isotropic properties. We can relate the pressure and volume of a gas with its average kinetic energy, as we saw this expression, and we can find the temperature of a gas if we know the average kinetic energy of the gas molecules. So this is a very important equation. Next class, we would like to answer these two questions here. First, how to calculate the velocity distribution of a given gas. Second, which factors can influence this distribution? These are important questions to answer. And finally, the reference. If the student would like to study a bit more, he would take one of these. I can suggest 2 books, there are many. And it's possible to watch this lecture at this homepage here. Thank you for your